2,000 meters beneath the surface of the Atlantic, south of Greenland, something is happening that no human eye will ever witness directly. Down there, in total darkness, enormous volumes of cold, dense water are slowly sinking and beginning a long journey south. Scientists call this process overturning, and it lies at the heart of one of the most important systems on the entire planet. A system that stayed almost invisible for centuries, hidden beneath the waves, yet one that today shapes the climate of hundreds of millions of people who have never heard its name. We tend to think of the ocean as something permanent. The sea looks today the way it looked 100 years ago. The same waves, the same horizon, the same smell of salt in the air. But behind that apparent stability lies a system that is slowly, quietly changing before our eyes. And what scientists have found over the past several months has led many of them to describe it in a single word: a warning. A warning the ocean has been sending for decades, but one that has grown considerably louder in recent months. We are talking about the Atlantic Meridional Overturning Circulation, usually shortened to AMOC, or described with a simpler image: the ocean's conveyor belt. It is not a single current, but an entire network of interconnected flows that carries heat from the tropics toward the northern latitudes, and then sends cold water back south through the deep ocean. The Gulf Stream, the current almost everyone has heard of, is only the surface-level, most visible part of this much larger system. To understand why this system matters so much, it helps to look at a map. London sits at roughly the same latitude as the southern shore of Hudson Bay in Canada, a place where winter temperatures regularly drop far below freezing. Yet London's climate is dramatically milder. That difference of dozens of degrees comes down to this circulation. Warm water rising from the tropics releases its heat into the atmosphere above the North Atlantic, warming Western Europe in the process. Without this mechanism, the climate of an entire continent would look fundamentally different. The system runs on a fairly simple physical principle, even though modeling its real-world behavior is extraordinarily difficult. Warm, salty water travels north along the ocean's surface. As it approaches the pole, it cools and becomes denser. And in specific regions, particularly the seas north and northwest of Iceland, along with the Labrador and Erminger seas, that dense water sinks to great depth. From there, it begins its slow return journey south, feeding into the deep currents of the entire global ocean. This sinking process, known as deep water formation, functions as the pump that drives the whole system forward. This is precisely why scientists have spent decades watching a small patch of ocean just south of Greenland and Iceland with particular attention. That patch earned an informal nickname, the cold blob, sometimes also called the North Atlantic warming hole. The name captures something genuinely strange about this spot. While the rest of the ocean has been gradually warming under the influence of climate change, this one region has been doing the opposite, cooling instead. Since the beginning of the 20th century, temperatures there have dropped by nearly 1 degree Celsius, even as the global average has risen considerably more than that over the same span of time. The anomaly first became visible on NASA's global temperature maps around the middle of the 2010s, when a small patch of blue stood out sharply against a map otherwise dominated by shades of orange and yellow, the colors used to represent warming. Back in 2015, It looked almost like a fluke, the one place on the planet that seemed to be moving against the overall trend. Ever since, researchers have been trying to understand what exactly was driving this unusual behavior in one particular stretch of the Atlantic. For a long time, two competing explanations circulated among scientists. The first pointed to the atmosphere. Stronger winds over the region could be increasing evaporation from the sea surface, and evaporation, in turn, cools the uppermost layer of the ocean. Additional cloud cover forming above this cooler patch could then reflect more sunlight back into space, reinforcing the cooling in a kind of self-sustaining loop that had little to do with what was happening deep below the surface. The second explanation was considerably more concerning. It suggested that the cold blob was not the result of local atmospheric quirks at all, but a direct reflection of what was happening at depth. If the Atlantic circulation were weakening, this region would simply receive less warm water arriving from the south. Less incoming heat would mean lower surface temperatures, which would make the cold blob not a strange weather anomaly, but something closer to a thermometer, one quietly reporting on the health of the entire circulation system. The debate between these two explanations continued for years without a clear resolution. There were too few direct observations, the system was too complex, and there were too many variables at play. But in the summer of 2026, a series of studies was published that meaningfully shifted the balance of evidence toward the second, more serious explanation. And it happened against a backdrop of events that were difficult for anyone to ignore. That summer, Europe was in the middle of its third major heat event of the year. Temperatures in France had touched 44 degrees Celsius. Cities across the continent were breaking records that had stood for only a few years before being broken again. And in the middle of this heat, researchers led by Stefan Rahmstorf at the Potsdam Institute for Climate Impact Research published a study in the journal Geophysical Research Letters that took direct aim at the old debate over the cold blob's origins. Rahmstorf's team did something earlier studies had not been able to do at the same scale. They combined 70 years of reanalysis data, records built from direct historical weather observations rather than climate model output alone, with measurements of ocean heat content collected by modern satellites and ocean instruments. Reanalysis data has a particular advantage in this kind of investigation. It is grounded in what was actually measured in the atmosphere and ocean at the time, rather than in a simulation of what might have happened. When the team examined this combined data set, the pattern that emerged was unambiguous. The cooling in the cold blob was not limited to the surface. It extended deep into the water column, well below where wind-driven evaporation or cloud cover could plausibly explain it. This detail mattered enormously. Surface-level atmospheric effects, by their nature, act primarily on the topmost layer of the ocean. If the cooling had been driven by stronger winds or extra cloud cover, the signal should have faded quickly with depth. Instead, the research team found that the cooling reached deep into the water, a pattern far more consistent with a reduction in the amount of warm water being carried into the region from the tropics. In their own words, the researchers described the finding as supporting the interpretation that the cold blob is a sign of a weakening AMOC, one that plays a major role in transporting heat into this specific corner of the North Atlantic. Rahmstorf himself is not a newcomer to this line of research. He has been studying the Atlantic circulation and its possible weakening for over 2 decades. And for much of that time, he approached the most alarming scenarios with real caution. That caution has shifted. In interviews accompanying the publication of the new research, He stated that he now considers the probability of an eventual AMOC shutdown to be higher than 50%, a marked change from his earlier, more conservative assessments. He was careful to frame this as his own probability estimate rather than a settled scientific consensus, since substantial uncertainty remains among researchers studying the system. But the shift in his own position reflected a broader shift taking place across the field. The Potsdam team's paper was not an isolated finding. It arrived alongside a second major piece of research published earlier that spring in the journal Science Advances. This one focused not on the cold blob specifically, but on refining projections for how much the AMOC might weaken by the end of this century. Earlier projections, built largely on climate models running independently of real-world observational data, had suggested a weakening in the range of 24 to 39% by 2100, depending on how aggressively greenhouse gas emissions continue to rise. The new study took a different approach, constraining these models using real-world measurements of sea surface temperature and sea surface salinity, essentially asking the models to match what has actually been observed, rather than relying purely on theoretical projections. The result was a substantially higher estimate. According to this refined modeling approach, the AMOC could weaken by approximately 51% by the year 2100, a reduction roughly 60% greater than what earlier model-only estimates had suggested. It is worth being precise about what this number does and does not mean. A 51% weakening is not the same as a complete collapse or shutdown of the system. It describes a significant slowdown in the volume of water being transported by the circulation, one that would still leave the AMOC functioning, but considerably less effectively than it does today. Even so, a reduction of this magnitude would represent a profound shift in how heat moves around the planet, with consequences reaching far beyond the North Atlantic itself. A third study, this one led by researchers at the University of Miami's Rosenstiel School of Marine, Atmospheric, and Earth Science, approached the question from an entirely different angle. Rather than relying on climate models or reanalysis data, this team worked directly with observational measurements collected at 4 separate latitudes across the Atlantic, spanning roughly 2 decades of continuous monitoring. Shane Elipott, a physical oceanographer at the University of Miami and one of the study's senior authors, explained that the significance of the findings lay precisely in this consistency. The team found evidence of weakening at every one of the 4 locations they examined, not just 1 or 2, which strengthened confidence that the pattern reflects a genuine, basin-wide trend rather than a localized fluctuation. The study focused specifically on the western boundary of the Atlantic, the region closest to North America, which Elipott described as something like an early indicator for the broader system, a place where changes tend to show up first and most clearly. The real-world data gathered by his team, he noted, helps validate the predictions generated by climate models, offering a kind of independent confirmation that the models are capturing something real rather than an artifact of their internal assumptions. René van Westen, a marine and atmospheric researcher at Utrecht University, who was not involved in the Miami study, described the findings as providing strong observational evidence that the present-day AMOC is indeed declining. A conclusion he noted was now supported by multiple independent lines of evidence, rather than resting on any single study. To understand why researchers are treating this pattern with such seriousness, it helps to step back and look at how long humanity has actually been watching the AMOC directly. Continuous, instrument-based monitoring of the circulation only began in 2004, with the installation of an array of sensors stretched across the Atlantic at approximately 26 degrees north latitude, a project known as RAPID, sometimes referred to by the fuller name Rapid Mocha. Before that date, essentially everything scientists knew about the strength of the AMOC came from indirect methods. Reconstructions based on temperature patterns, salinity records, and various proxy measurements taken from sediment cores and other indirect sources. This means that as of 2026, the rapid array has been running for just over 2 decades, a span of time that is, in the language of ocean and climate science, still relatively short. Ocean circulation naturally fluctuates across multiple timescales, some tied to seasons, others to multi-year or even multi-decade cycles driven by patterns like the North Atlantic Oscillation. Distinguishing a genuine long-term decline from this kind of natural variability requires a long enough observational record. And for years, many scientists were cautious about drawing firm conclusions from data that spanned barely more than a decade. Interestingly, Rapid's own early records showed the AMOC weakening between 2004 and 2012, only to partially recover in the years that followed, a pattern that at the time fed into the argument that the system's natural variability might be large enough to explain what looked like a downward trend. What has changed more recently is the length of the observational record itself. 22 years, while still short by the standards of long-term climate science, is now approaching the point where researchers feel more confident distinguishing a genuine multi-decadal trend from short-term noise. Combined with reconstructions using sea surface temperature fingerprint patterns, a technique that estimates AMOC strength indirectly by analyzing characteristic temperature patterns across the North Atlantic, longer-term estimates now suggest the circulation has weakened by roughly 3 sverdrups, give or take 1 sverdrup, since around 1950. A sverdrup, the standard unit oceanographers use to measure the volume of water moving through a current, equals 1 million cubic meters per second, an almost incomprehensible volume when translated into more familiar terms. Some paleoclimate research goes further still, suggesting that the AMOC may currently be in its weakest state in over 1,000 years, based on evidence drawn from sediment cores, ice cores, and other indirect indicators that allow scientists to reconstruct ocean conditions stretching back well before the era of direct measurement. This kind of long-term perspective matters because it helps place the recent decline within a much broader historical context. A weakening trend that might look modest or ambiguous over 20 years takes on a different character when placed against a backdrop of a millennium. None of this observational evidence, however, is what has driven the more urgent tone in recent scientific communication. That shift comes from a different, more specialized area of research: the search for what scientists call early warning signals of an approaching tipping point. A tipping point, in the specific technical sense used by climate scientists, refers to a threshold beyond which a system shifts relatively abruptly from one stable state to a different one, and where that shift, once triggered, becomes very difficult or even effectively impossible to reverse on any timescale relevant to human civilization. The AMOC has long been considered one of the clearest candidates for this kind of behavior among Earth's major climate systems, largely because of a well-understood physical mechanism at its core. The circulation depends on dense, salty water sinking in the North Atlantic. Add enough fresh water to that region, whether from melting ice sheets, increased rainfall, or river runoff, and the water becomes less dense, less able to sink, and the entire pump that drives the system can begin to falter. Past a certain threshold, models suggest the system could shift into a much weaker or even fully collapsed state relatively quickly, and once there, it might not simply switch back once conditions improve. A landmark study published in 2023 by Peter and Suzanne Ditlevsen at the University of Copenhagen attempted to put a number on this risk using purely statistical methods, independent of the physics-based climate models researchers typically rely on. Their approach searched historical sea surface temperature data for two specific statistical signatures associated with systems approaching a tipping point: rising variance, meaning the system's behavior becomes more erratic and unpredictable as it loses resilience, and rising autocorrelation, meaning the system takes progressively longer to recover from small disturbances, a phenomenon researchers call critical slowing down. Both signals, they found, were clearly present and increasing in the historical AMOC data. Based on these trends, the Ditlevsens estimated that a collapse could occur around the middle of this century under current emissions trajectories, a projection dramatically earlier than the timeline suggested by most standard climate models, which had generally treated a full collapse within the 21st century as unlikely, if not impossible, to rule out entirely. That study drew considerable attention and, predictably, considerable pushback. Many scientists in the field, while acknowledging the value of statistical early warning methods, argued that applying them to a system as complex and noisy as the AMOC, using a historical record still relatively short and drawn largely from indirect proxy data, carries substantial uncertainty. The Intergovernmental Panel on Climate Change, in its most recent major assessment report, reflected this tension directly. It expressed high confidence that the AMOC would weaken over the 21st century as a general, qualitative feature of a warming world, a conclusion supported by strong physical reasoning and broad agreement across models. At the same time, it expressed comparatively low confidence in any specific quantitative projection of exactly how much weakening to expect, or precisely when any tipping point, if one exists, might be crossed. This distinction between confidence that something is happening and considerably lower confidence about exactly how fast or how far it will go runs through nearly all of the credible scientific literature on this topic, and it deserves to be stated plainly rather than glossed over. Dr. Laura Jackson of the UK Met Office, explaining why the AMOC resists simple modeling, has pointed out that the AMOC is not one single discrete thing that can be measured and projected in isolation. It is better understood as the combined result of many different interacting currents, driven by wind patterns, temperature gradients, and salinity differences that themselves respond to a huge range of other factors. Modeling all of these interacting pieces accurately and projecting how they will behave decades into the future under a changing climate remains one of the genuinely hard problems in Earth system science. More recent research has continued to refine this picture in both directions. A preprint study circulated in January 2026 using very high-resolution ocean modeling capable of capturing small-scale eddies and currents that coarser models simply cannot resolve, suggested that the AMOC's sensitivity to meltwater from Greenland may be considerably higher than earlier, lower-resolution simulations had captured, implying that a collapse could be more likely than previously modeled. Other high-resolution modeling work, however, examining the AMOC's response to Greenland meltwater specifically within a strongly eddying ocean model, has found a comparatively weak response over the 21st century, illustrating just how much the details of a given model's construction can shape its conclusions. This is, in short, an active and genuinely unsettled area of research, not a field in which every study points cleanly in the same direction. One particular projection has attracted significant public attention. An estimate suggesting an AMOC collapse could occur as early as 2065, a date that was itself revised earlier from a previous estimate of 2057. It is worth being clear that this specific projection has drawn considerable skepticism from other scientists in the field, many of whom view it as an outlier at the more alarming end of a wide range of possible outcomes, rather than a central consensus estimate. The honest scientific picture, as of the middle of 2026, is one of a system that is very likely weakening, probably at a rate faster than earlier models suggested, with a genuine and non-trivial risk of an eventual tipping point, but with considerable unresolved uncertainty about exactly when that point might be reached, or whether it will be reached at all, within a time frame relevant to anyone alive today. Despite this uncertainty over timing, the scientific community has become considerably more vocal about the stakes involved. In October 2024, a group of 44 climate scientists published an open letter arguing that the risk of an AMOC collapse had been significantly underestimated in mainstream climate assessments, and that such a collapse could plausibly occur within the coming decades, rather than being safely confined to the more distant future. The letter specifically called on Nordic countries, whose climates would be especially affected by any weakening of the system, to push for stronger implementation of the Paris Agreement as a means of reducing the risk. The Nordic Council itself, representing Denmark, Iceland, Norway, Sweden, and Finland, along with several associated territories, issued its own warning that winter temperatures in Iceland could fall dramatically under a weakened or collapsed AMOC scenario. A stark illustration of how directly this abstract oceanographic system connects to the everyday experience of people living around the North Atlantic. So what precisely would change if this weakening continues, or if the system eventually crosses some kind of threshold? The honest answer is that the consequences would not be limited to a single region or a single type of impact. They would ripple outward across weather patterns, sea levels, agriculture, and ocean ecosystems on multiple continents, though the scale and certainty of each individual consequence varies considerably. Europe sits closest to the center of this story, and for good reason. The same heat that carries the North Atlantic's warmth toward Western Europe today is precisely what a weakened AMOC would deliver less of over time. Researchers describing a full shutdown scenario, as opposed to a partial weakening, have pointed to substantially colder winters across Northern Europe as one of the more likely outcomes, a genuine reversal of the mild maritime climate that countries like the United Kingdom, Ireland, and the Nordic nations have relied on for centuries. Don Chambers, an oceanographer at the University of South Florida, summarized the expected effect of a slowing AMOC in strikingly simple terms. Cooler winters and summers around the North Atlantic, paired with small but locally significant increases in sea level along the North American coast. There is a genuine paradox buried in this picture, though, one that has only become clear through research conducted over just the past few years, and it deserves careful explanation, because it runs counter to the intuitive assumption that a cooling ocean should mean a cooling continent. Marilena Oltmans, an ocean and climate physicist at the University of Bremen, has led research showing that the cold blob itself, rather than simply threatening Europe with future cold, is actively contributing to some of the extreme heat events the continent has already experienced. The mechanism works through the atmosphere rather than direct heat transfer. The sharp temperature contrast between the unusually cold waters of the cold blob and the warmer water surrounding it creates a strong thermal boundary in the ocean surface. That boundary, in turn, acts something like a guide rail for the jet stream, the high-altitude river of fast-moving air that governs much of Europe's day-to-day weather. Rather than flowing directly across the continent from west to east, as it more typically would, the jet stream tends to bend sharply northward around this cold anomaly, arcing up and over it before continuing on. When that happens, it can leave a gap over Western and Central Europe, where a high-pressure system is free to settle in and remain largely undisturbed, trapping heat beneath it for extended periods. The classic setup meteorologists refer to as a heat dome. Gerard McCarthy, an oceanographer at Maynooth University in Ireland, put the apparent contradiction plainly. A cold Atlantic does not necessarily mean a colder Europe. Some of the continent's most extreme heat events, he noted, may actually be worsened, not softened, by the presence of this cold patch just offshore. A separate line of research published back in 2016 had already identified cold anomalies in this same general region as a common precursor to major European heat waves reaching back to the 1980s, lending additional support to a connection that once seemed almost counterintuitive. It is important to be precise about what this means and does not mean. This finding does not suggest that a weakening AMOC is, on balance, good news for Europe, nor does it cancel out the risk of harsher winters under a more extreme, long-term weakening scenario. Rather, it illustrates just how complicated the relationship between ocean circulation and regional weather actually is. A slowing AMOC appears capable of contributing to both ends of the temperature spectrum, intensifying summer heat in the near term through its effects on atmospheric circulation, while simultaneously raising the long-term risk of substantially colder winters if the weakening trend continues or accelerates toward anything resembling a full shutdown. Sea level rise represents a second major consequence, and one with a more straightforward physical explanation. The AMOC, among its other roles, effectively piles up water against the eastern seaboard of North America as part of its normal circulation pattern. When the circulation weakens, that effect diminishes, and sea levels along stretches of the U.S. East Coast can rise noticeably faster than the global average. A study published in 2015 in the journal Nature identified a roughly 30% downturn in AMOC strength during 2009 and 2010 as one of two contributing factors behind an unprecedented 128mm jump in sea level recorded north of New York City over just that 2-year span, an event researchers described at the time as without clear historical precedent. Subsequent research examining the mechanism behind this link found that reduced deep water formation, tied directly to a weaker AMOC, allows warmer water to accumulate below the surface along the coast, a process that appears to compound with the effects of rising carbon emissions more generally, to push regional sea level rise well above the global average pace. Beyond Europe and the Atlantic coastline of North America, the effects of a weakening AMOC extend into regions that, at first glance, seem to have little connection to a current system thousands of kilometers away. One of the more significant of these concerns the monsoon systems that hundreds of millions of people across South Asia and parts of Africa depend on for agriculture and, in many cases, basic water security. The AMOC plays a role in the broader global heat balance that helps determine where the intertropical convergence zone, the band of intense rainfall that shifts seasonally and drives monsoon patterns, sits at any given time of year. A significant weakening of the AMOC could shift this band in ways that disrupt monsoon timing and intensity across the Indian subcontinent and the Sahel region of Africa, potentially triggering prolonged droughts in areas where rainfall variability already represents an existential concern for agricultural communities. Some research has gone as far as linking the cold blob specifically to detectable shifts already occurring in the Indian summer monsoon, a system relied upon by more than 1 billion people for their food and water supply. Agriculture closer to the North Atlantic itself would also face substantial disruption under a more extreme weakening scenario. A study published in 2020 in the journal Nature Food modeled the agricultural consequences of a full AMOC collapse and found that such a scenario could lead to a widespread cessation of arable farming across the United Kingdom, alongside broader losses in agricultural output, potentially an order of magnitude larger than what climate change is otherwise projected to cause in the region through warming alone. The mechanism here connects back to temperature. A full AMOC collapse would be expected to substantially shorten Britain's growing season and increase the frequency of damaging frosts, conditions that many current crop varieties and farming systems are simply not equipped to handle at scale. Ocean ecosystems represent another dimension of this story that receives comparatively less public attention, but carries significant weight among marine scientists. The regions where deep water formation occurs, particularly the Nordic Seas and the waters around the Labrador and Erminger Seas, are associated with intense vertical exchanges of heat, dissolved oxygen, carbon, and essential nutrients between surface and deep waters. These exchanges support some of the most biologically productive fisheries in the North Atlantic. A weakened circulation would be expected to reduce this vertical mixing, potentially lowering oxygen levels in parts of the deep ocean and disrupting the nutrient cycles that support fish populations many coastal communities depend on economically. The AMOC additionally functions as one of the ocean's major mechanisms for absorbing carbon dioxide from the atmosphere, meaning a weakened circulation could, over time, somewhat reduce the ocean's overall capacity to act as a carbon sink, adding a subtle but real feedback into the broader climate system. Given the scale and reach of these potential consequences, one might reasonably ask what is being done to track this system more closely as concerns mount. Here the story takes an unexpected and, to many researchers, deeply frustrating turn. In early June 2026, the United States government announced plans to decommission and physically remove a substantial portion of its ocean monitoring infrastructure across the Atlantic and Pacific, a program known as the Ocean Observatories Initiative, citing budgetary constraints as the primary rationale. Among the roughly 900 deep-sea instruments slated for removal under this plan are moorings located in the Erminger Sea, one of the handful of locations on the planet where surface water actually completes the sinking process that powers the AMOC's deep return flow. These particular instruments provide some of the only direct continuous observational data available anywhere on the strength and variability of deep water formation, the physical process that sits at the very center of essentially every serious AMOC collapse scenario that has been modeled. Removing them would not eliminate scientists' ability to study the AMOC entirely, since other monitoring arrays, including the Rapid Array at 26 degrees north, would remain in place. But it would create a meaningful gap in the observational record at precisely the location and moment when that data is arguably most needed, just as the 22-year rapid record is finally becoming long enough to help distinguish genuine long-term trends from short-term natural variability. Several oceanographers have voiced concern that this timing could not be worse from a scientific standpoint, arguing that reducing observational capacity now, just as evidence of accelerating change is mounting, And just as the tools for detecting genuine tipping point behavior are becoming more capable, risks leaving researchers with meaningfully less information, precisely when more is needed. It is worth noting that this decision remains a live policy matter rather than a settled scientific one, and its ultimate scope, along with how it will affect long-term AMOC monitoring specifically, may still evolve as the plan moves toward implementation. Faced with genuine scientific uncertainty about timing, but a growing body of evidence pointing toward a real and worsening trend, what options exist for reducing the risk of the more severe outcomes under discussion? Rahmstorf, reflecting on his own research alongside decades of broader work on this subject, has repeatedly returned to a fairly direct answer. The single most effective lever available remains adherence to the emissions reduction targets originally laid out in the Paris Agreement. The physical mechanism driving AMOC weakening traces back most directly to freshwater input from melting ice, particularly the Greenland ice sheet, and to broader ocean warming, both of which are governed substantially by the trajectory of global greenhouse gas emissions. Slower warming means less ice melt, which means less freshwater disruption to the delicate salinity balance that keeps the circulation's sinking mechanism functioning. In this sense, the fate of the AMOC is not a separate crisis unfolding independently of the broader climate conversation, but one of its more consequential downstream effects. Rahmstorf has also been candid about where the world currently stands relative to that target, acknowledging in 2026 that global temperatures have likely already crossed the Paris Agreement's 1.5 degrees Celsius warming threshold on a sustained basis, a milestone that arrived earlier than many earlier projections had anticipated. This does not render further mitigation efforts meaningless. Every fraction of a degree of additional warming avoided still translates into reduced ice melt, reduced freshwater input into the North Atlantic, and by extension, a somewhat lower risk of pushing the AMOC toward the more severe end of its range of possible futures. But it does mean that the conversation among scientists studying this system has increasingly shifted from purely preventing change toward also preparing for a world in which some degree of AMOC weakening is now effectively locked in, regardless of what emissions trajectory the world follows from this point forward. It is worth stepping back at this point to place all of this within appropriate context. The AMOC is not projected to collapse next year, next decade, or with any confidence within a specific near-term time frame at all. The most credible, broadly supported scientific assessments continue to describe a system that is very likely weakening gradually, with a genuine, non-negligible, but still highly uncertain risk of a more dramatic shift occurring at some point within this century. That is a materially different picture from the more dramatic framing that sometimes circulates in less careful media coverage, where a starker binary of imminent collapse versus complete safety tends to obscure the considerably more nuanced reality that researchers themselves describe. At the same time, this is precisely why the language scientists have chosen matters. When David Thornalley, a professor of ocean and climate science at University College London, who was not involved in the Potsdam study, reviewed its conclusions, he offered a characteristically careful assessment. The study, he said, strengthens the case linking the cold blob to a weakening AMOC, but he cautioned that the sparseness of real-world observational data in this part of the ocean means the available datasets are best treated as good approximations of reality rather than perfect representations of it. This kind of qualified language, common throughout the peer-reviewed literature on this topic, reflects genuine scientific caution rather than any attempt to downplay the underlying concern. Researchers are, in effect, saying two things simultaneously. The direction of change is now reasonably well established, while the precise magnitude, timing, and ultimate endpoint of that change remain genuinely open questions. To appreciate why scientists take even a partial AMOC weakening so seriously, it helps to look further back than the 20th century, into the deeper climate history preserved in ice cores and ocean sediment records. The geological record contains clear evidence that the AMOC has not always operated the way it does today, and that it has, in the past, undergone genuinely abrupt shifts. During the last ice age, a period known to paleoclimatologists as the Younger Dryas, roughly 12,000 years ago, evidence suggests the AMOC weakened dramatically and rapidly, plunging the North Atlantic region back into near glacial conditions for well over 1,000 years, all while the rest of the planet was in the process of warming out of the Ice Age. The leading explanation for what triggered this episode involves a massive pulse of fresh meltwater draining from collapsing ice sheets into the North Atlantic, disrupting the same salinity-driven sinking mechanism that scientists worry about today, albeit at a scale considerably larger than anything currently underway. This ancient event, and others like it identified in the sediment record and known collectively as Dansgaard-Oeschger events, serve an important function in the current scientific conversation. They demonstrate, through direct physical evidence rather than modeling alone, that the AMOC is a system genuinely capable of rapid, large-scale reorganization under the right conditions, rather than a purely theoretical possibility confined to computer simulations. This is a meaningfully different kind of evidence than a model projection, since it reflects something that has actually happened on this planet under broadly comparable physical mechanisms, even if the specific triggers and timescales involved differ from the present situation in important ways. It is worth noting, however, that recent research examining sediment and microfossil records from the depths of the last ice age has also found that some version of the AMOC persisted even through extremely cold glacial conditions, suggesting the system possesses a degree of underlying resilience alongside its capacity for abrupt change, a nuance that complicates any simple narrative in either direction. The physical chain of cause and effect connecting rising global temperatures to a weakening AMOC runs through several interlinked steps, and walking through each one helps clarify exactly where the scientific uncertainty in this story actually sits. The first step is well established. Rising global temperatures are accelerating the melting of the Greenland ice sheet, a process documented extensively through satellite gravity measurements and direct surface observations over more than 2 decades now. The second step, that this meltwater flows into the North Atlantic and reduces surface salinity in key sinking regions, is a matter of basic physics and is not seriously disputed. The third step, that reduced salinity makes surface water less dense and therefore less able to sink, forming the physical basis for AMOC weakening, is likewise grounded in well-established oceanographic principles. Where the genuine uncertainty concentrates is in the fourth and fifth steps. Precisely how sensitive the overall circulation is to a given amount of freshwater input, and whether that sensitivity is roughly linear, meaning gradual weakening proportional to meltwater input, or whether it contains a genuine threshold effect, meaning the system could behave in a stable, only gradually changing manner right up until a critical point is crossed, after which it shifts relatively abruptly into a different state. This is fundamentally a question about the underlying physics and dynamics of a genuinely complex fluid system. one that even the most sophisticated ocean models available today struggle to represent perfectly. Partly because capturing the small-scale ocean eddies and mixing processes that influence this behavior requires computational resolution that remains challenging even for the most powerful supercomputers currently available to climate researchers. This computational challenge has, in recent years, given rise to an entire subfield dedicated to building higher-resolution ocean models specifically capable of resolving these finer-scale processes, and the results so far have been genuinely mixed rather than uniformly pointing toward either more or less alarm. One line of high-resolution modeling work, examining how the AMOC responds to Greenland meltwater within an ocean model designed to capture strong eddy activity, found a comparatively muted response through the 21st century, suggesting the system might prove somewhat more resistant to disruption than some coarser, lower-resolution models had implied. Other high-resolution efforts, including the January 2026 preprint mentioned earlier, arrived at the opposite conclusion, finding heightened sensitivity to meltwater and a correspondingly higher collapse risk. Reconciling these differing results remains an active area of ongoing research, and it would be inaccurate to characterize the field as having settled on a single, unified answer regarding exactly how sensitive the AMOC truly is. This kind of open disagreement between serious, peer-reviewed studies is not a sign that the underlying science is unreliable or that concerns about AMOC weakening should be dismissed. It is rather a fairly ordinary feature of active scientific research into a genuinely difficult problem, one involving a system that is simultaneously enormous in physical scale, extremely complex in its internal dynamics, and still comparatively brief in its observational record. Climate science as a broader field has navigated similar periods of internal disagreement before, on questions ranging from the precise sensitivity of global temperature to rising carbon dioxide concentrations, to the exact rate of ice sheet loss in Antarctica. And in most of these cases, the range of scientific uncertainty has narrowed over time as observational records lengthened and modeling techniques improved, even when the broad direction of change was already reasonably clear from early on. The AMOC is often discussed alongside several other so-called tipping elements identified within the Earth's broader climate system, and placing it within that wider context helps illustrate both its distinctiveness and its shared features with other major systems under similar scrutiny. The Greenland and West Antarctic ice sheets, both of which hold enough frozen water to raise global sea levels by multiple meters if they were to melt substantially, are considered tipping elements, largely because ice loss tends to become self-reinforcing past certain thresholds, as lower ice sheet elevation exposes the remaining ice to warmer air, accelerating further melting in a feedback loop. Coral reef systems worldwide represent another widely discussed tipping element, with widespread bleaching events triggered by ocean warming threatening to push many reef ecosystems past a point of viable recovery. The Amazon rainforest is sometimes described in similar terms, given research suggesting that sufficient deforestation combined with changing rainfall patterns could push large sections of the forest past a threshold beyond which they can no longer sustain themselves as rainforest, and would instead transition toward a drier, savanna-like ecosystem. Some more recent research has additionally suggested that the overturning circulation in the Southern Ocean surrounding Antarctica may actually be more prone to a tipping point-style collapse than the AMOC itself, a comparatively newer area of research receiving increasing scientific attention as more observational data becomes available from that considerably more remote and historically under-monitored region. What connects all of these systems, including the AMOC, is a shared characteristic. Each involves a physical process capable of self-reinforcing feedback loops. Each carries the theoretical potential for relatively abrupt, difficult-to-reverse change once a critical threshold is crossed. And each remains subject to genuine, still unresolved scientific uncertainty regarding exactly where that threshold sits and how close current conditions actually are to it. One additional dimension worth addressing directly, precisely because it tends to generate the most public speculation, involves several more unconventional or exploratory proposals that have surfaced in discussions about AMOC risk mitigation. Various researchers and engineers have floated the idea of large-scale geoengineering interventions, ranging from artificial structures designed to block or slow freshwater outflow from Greenland's melting ice sheet, to proposals for enormous underwater barriers spanning parts of the Atlantic or Arctic, designed to influence broader ocean circulation patterns and heat exchange, including a widely discussed concept for a massive dam-like structure spanning the Bering Strait between Alaska and Russia. None of these proposals has moved meaningfully beyond the conceptual or early feasibility stage, and virtually all serious oceanographers who have commented on them describe the engineering, financial, and geopolitical obstacles involved as immense, likely placing any such intervention well beyond realistic consideration on any timescale relevant to the AMOC concerns being discussed today. They are worth mentioning primarily because they illustrate just how seriously some researchers and engineers are treating the underlying risk, even if the specific proposed solutions remain firmly speculative. Returning to the more immediate and grounded science, it is worth examining in a bit more detail exactly how researchers go about measuring something as vast and largely invisible as an ocean current spanning an entire ocean basin. The rapid array at 26 degrees north, the longest continuous direct measurement record available for the AMOC, does not work by physically tracking individual parcels of water as they move. Instead, it relies on a network of moored instruments stretched across the full width of the Atlantic at that latitude, from the coast of Florida to the coast of Africa, measuring temperature, salinity, and pressure at various depths continuously over time. From these measurements, combined with additional data on currents flowing through the Florida Straits and wind-driven surface transport, oceanographers can calculate the net volume of water moving northward versus southward across that entire transect, arriving at an estimate of overall AMOC strength expressed in spheredrups. This approach has real strengths, offering a continuous, direct, physically grounded measurement rather than a model-based estimate or an indirect proxy. But it also has real limitations. It provides a single snapshot of circulation strength at one specific latitude. And while that latitude was chosen deliberately because it captures a substantial share of the overall circulation, it cannot fully capture what is happening at other critical points in the system, including the deep water formation regions further north, where the circulation's driving mechanism actually originates. This is precisely why the Erminger sea moorings discussed earlier carry such particular scientific value, and why their planned removal has drawn specific concern from researchers who understand exactly what kind of data would be lost. Complementing RAPID, researchers have also developed methods to estimate historical AMOC strength indirectly, reaching back further than any direct instrument record could allow. The sea surface temperature fingerprint method, mentioned earlier in connection with the roughly 3 spheredrup weakening estimated since 1950, works by identifying a specific spatial pattern of temperature change across the North Atlantic that climate models consistently associate with AMOC strength, essentially the cold blob pattern itself. and then tracking how strongly that pattern has appeared in the historical temperature record stretching back over a century. This method carries its own uncertainties, since it relies on the assumption that the relationship between this particular temperature pattern and actual AMOC strength has remained stable over the entire period being examined, an assumption that cannot be independently verified using direct measurements from earlier decades when no such measurements existed. Sediment core and other paleoclimate proxy methods extend the observational reach further still, in principle allowing researchers to reconstruct AMOC behavior across thousands of years. But these methods rely on indirect chemical and physical signatures preserved in ocean sediments, ice cores, and other natural archives, introducing yet another layer of interpretive uncertainty regarding exactly how faithfully these proxies track the specific physical quantity researchers are ultimately interested in. Taken together, these three broad categories of evidence, direct instrument measurement, temperature pattern-based reconstruction, and deep paleoclimate proxy records, form a kind of converging body of evidence. No single method is definitive on its own, but the fact that multiple independent approaches, each with different strengths, weaknesses, and sources of potential error, point toward a broadly consistent conclusion is precisely what has shifted scientific opinion meaningfully over the past several years. It is this convergence, more than any single headline-grabbing study, that best explains why language among AMOC researchers has grown noticeably more direct over roughly the past 2 to 3 years. The authors of the 2026 Potsdam study themselves wrote plainly that the risk they were describing requires urgent attention from political decision-makers. Language that stands in fairly clear contrast to the more heavily hedged, cautious phrasing that characterized much of the AMOC literature from a decade or more earlier. This shift in tone reflects the accumulation of evidence across multiple independent lines of research, rather than any single dramatic new finding. And it is worth taking seriously precisely because scientific communities, and the physical scientists working within them in particular, tend toward institutional caution rather than premature alarm, given the professional and reputational costs associated with overstating uncertain conclusions. At the same time, responsible science communication requires holding two things in mind simultaneously, without collapsing one into the other. The underlying trend toward AMOC weakening now rests on a genuinely broad and strengthening evidentiary foundation, while the precise timeline, ultimate magnitude, and specific regional consequences of that weakening remain subjects of legitimate, ongoing scientific debate and research. Neither the more measured framing favored by some scientific bodies, nor the more urgent framing favored by others, should be read as contradicting the other. They largely reflect differing emphases on which aspect of a complex, still unfolding picture deserves the most attention at any given moment, rather than fundamentally different underlying assessments of the physical evidence itself. For people living far from the North Atlantic coastline, all of this can understandably feel abstract, a story unfolding at a scale and depth entirely removed from everyday experience. But the practical implications, should the weakening trend continue on anything resembling its currently observed trajectory, would eventually touch far more than European winters or East Coast tide gauges. Global shipping lanes, fisheries management policy, insurance markets pricing coastal flood risk, and agricultural planning across multiple continents would all, over time, need to account for a North Atlantic region behaving in ways that depart meaningfully from the relatively stable baseline that industrial civilization has built its infrastructure and expectations around over the past century and a half. None of these adjustments would need to happen overnight, and the gradual, decades-long nature of the changes being discussed does allow meaningful time for planning and adaptation, provided that planning begins early enough and draws on accurate, well-communicated science rather than either dismissive complacency or exaggerated alarm. It is worth pausing here to address a question that inevitably arises whenever a topic like this reaches a wider audience. How should someone without a background in oceanography or climate science actually think about a story this complex? One where legitimate researchers openly disagree on important details, even while broadly agreeing on the underlying direction of change. The most defensible approach probably involves resisting the pull toward either of the two simplest, most emotionally satisfying narratives. One narrative treats the entire subject as a settled, imminent catastrophe, an interpretation that outruns what the actual peer-reviewed evidence currently supports, and risks generating a sense of hopeless inevitability that serves no one well, least of all the broader effort to reduce emissions and slow the underlying warming trend. The other narrative dismisses the entire concern as speculative alarmism unworthy of serious attention, an interpretation that ignores a genuinely substantial and strengthening body of observational evidence, along with the explicit, carefully worded concerns of the researchers who have spent their careers studying this exact system. The more accurate picture sits between these two poles, closer to what the scientists themselves have actually said when speaking carefully and specifically. The Atlantic Meridional overturning circulation is very likely weakening, and the observational evidence supporting that basic conclusion has grown substantially stronger and more consistent over the past several years, converging across multiple independent methods of measurement and reconstruction. The rate and ultimate extent of that weakening remain genuinely uncertain, with credible projections ranging from a moderate multi-decade slowdown to something considerably more severe, and a meaningful, non-negligible chance, though far from a certainty, of the kind of relatively abrupt tipping point behavior that has occurred in this same physical system during past periods of Earth's climate history. The consequences of continued weakening, should it occur, would be genuinely significant and would extend well beyond the North Atlantic region itself, touching weather patterns, agriculture, sea levels, and ocean ecosystems across multiple continents, though the precise severity of each specific consequence likewise carries its own range of scientific uncertainty. Perhaps the most useful way to think about the cold blob and the broader body of research surrounding it is not as a definitive verdict, but as exactly what its informal nickname among some researchers suggests: a warning sign, a visible symptom on the surface of the ocean pointing toward changes unfolding largely out of sight, thousands of meters below. Warning signs, by their fundamental nature, do not tell us precisely what will happen or exactly when it will happen. What they do is indicate that close, sustained attention is genuinely warranted, that the underlying system is behaving differently than it once did, and that decisions made in the coming years regarding both global emissions and the maintenance of the very observational infrastructure needed to keep tracking these changes accurately will meaningfully shape which of the many currently plausible futures for this system ultimately comes to pass. The ocean has been sending signals about its own internal workings for longer than scientific instruments have existed to properly record them, embedded in sediment layers, locked into ice cores, and preserved in the geological record of past abrupt climate shifts, stretching back tens of thousands of years. What has changed in the past several years is not the ocean itself, which continues operating according to the same physical laws it always has, but rather the growing sophistication and reach of the tools available to actually read those signals with meaningful clarity. Satellites now track sea surface temperature with a level of global, continuous coverage that would have been simply unimaginable to oceanographers working just a few decades ago. Reanalysis techniques now allow researchers to reconstruct historical atmospheric and ocean conditions with a level of detail and consistency that earlier generations of scientists could only have approximated through sparse, scattered point measurements. High-resolution ocean models, running on computing infrastructure that continues to grow more powerful year over year, can now simulate physical processes at scales that were computationally out of reach even a decade ago. Taken together, these advances mean that the picture scientists have of the AMOC today, imperfect and still evolving as it undoubtedly is meaningfully clearer than the picture available even 10 years ago, when much of the debate over the cold blob's origins remained genuinely unresolved, and the observational record from the rapid array was still too short to distinguish long-term trend from short-term variability with real confidence. That improving clarity is, in itself, a reasonably encouraging development, even against the backdrop of a story that carries real cause for concern. Better information, consistently, leads to better decisions. Whether those decisions involve national climate policy, infrastructure planning along vulnerable coastlines, agricultural adaptation strategies in regions dependent on monsoon rainfall, or simply a more accurate public understanding of a system that will likely remain a subject of active scientific investigation and periodic new headlines for years to come. It is worth remembering, too, that the AMOC has weakened and strengthened before across the vast sweep of Earth's climate history, responding to ice ages, interglacial warm periods, and the abrupt meltwater pulses that punctuated the transition out of the last glacial period. The system possesses a degree of underlying physical resilience alongside its documented capacity for occasional abrupt change. And the geological record shows that even during the depths of the last ice age, some version of this circulation persisted rather than shutting down entirely. This is not offered as a reason for complacency, since the current situation involves a rate of change driven by human greenhouse gas emissions that differs meaningfully from the slower, largely natural forcings that drove most past AMOC variability. But it does offer useful context. This is a physical system with genuine internal dynamics and a long history of responding to changing conditions, not a fragile hair-trigger mechanism poised to collapse catastrophically at the slightest disturbance. What happens next depends on a combination of factors that are, in different ways, both within and beyond immediate human control. The physical sensitivity of the AMOC to continued freshwater input from Greenland's melting ice sheet is a property of the ocean system itself, one that ongoing research continues to refine but cannot simply choose to change. The rate at which that ice sheet continues to melt, however, along with the broader trajectory of global ocean warming, remains directly tied to the pace of global greenhouse gas emissions, a factor that does remain, at least in principle, within the realm of collective human decision-making. And the quality and continuity of the observational data available to track these changes as they unfold, information that shapes every projection and every policy decision built upon it, depends directly on choices about funding and maintaining the kind of long-term ocean monitoring infrastructure whose partial dismantling was announced earlier this year. None of these three factors operates in isolation from the others, and none offers a simple, singular lever that guarantees any particular outcome. But together they outline the rough contours of what comes next for this story. Continued scientific research working to narrow the remaining uncertainties. Continued global efforts, however imperfect and however contested, to slow the pace of greenhouse gas emissions and the ocean warming they drive. And an ongoing, genuinely open question about whether the observational tools needed to track this system with the necessary precision will remain available and adequately funded in the years immediately ahead, precisely when that data may matter most. For now, 2,000 meters beneath the waves south of Greenland, the same slow, largely invisible process continues, as it has for thousands of years. Warm water gradually cooling, growing denser, and beginning its long descent into the deep ocean. Whether that process continues at roughly its current pace, gradually weakens over the coming decades in a manner broadly consistent with existing projections, or approaches something closer to the more abrupt threshold that both the geological record and modern statistical early warning research suggest is at least physically possible, remains genuinely unknown. What is known, with a degree of confidence that has grown steadily stronger over the past several years of accumulating, converging evidence, is that the system is changing, that the ocean has been registering that change in measurable, physical ways for decades now, and that scientists studying it closely are increasingly, and in their own carefully chosen words, describing what they see as a warning worth taking seriously. There is one final thread worth drawing out before closing this account, because it speaks directly to how science itself progresses on questions of this scale and complexity. The debate over the coal blob's origins, wind and cloud effects versus a genuinely weakening circulation, took the better part of a decade to move meaningfully toward resolution. Not because any single research team was careless or slow, but because the underlying question required exactly the kind of patient, incremental accumulation of evidence that complex Earth systems typically demand. Satellite records needed to lengthen. Reanalysis techniques needed to mature. Computing power needed to advance to the point where researchers could meaningfully separate surface-level atmospheric noise from deeper, slower-moving ocean signals. Each of these developments arrived gradually, through the ordinary, largely unglamorous work of building instruments, maintaining monitoring networks, refining statistical methods, and publishing incremental findings that individually move the needle only slightly, but that collectively, over roughly a decade, shifted the scientific consensus from genuine uncertainty toward a considerably more confident, evidence-backed conclusion. That same pattern is likely to define how the remaining open questions about AMOC timing and magnitude eventually get resolved as well, assuming the observational tools required to do so remain in place and adequately funded. There will not be a single definitive study that settles the matter once and for all, arriving with perfect clarity on some specific future date. Instead, the picture will most likely continue sharpening gradually, year by year, as the rapid array's continuous record grows longer, as reanalysis techniques and high-resolution models continue improving, and as researchers around the world continue publishing findings that, individually modest, collectively narrow the range of remaining uncertainty a little further with each passing year. It is this gradual, cumulative, distinctly unglamorous process, rather than any single dramatic breakthrough, that will most likely determine how well prepared the world actually is when the fuller picture of the Atlantic's future finally comes into clearer focus. Until then, the warning stands largely where it has stood for the past several years, not as a certain prophecy of imminent catastrophe, and not as a speculative concern safely dismissed, but as a genuinely serious, evidence-backed signal from a system that regulates the climate of an entire ocean basin, urging closer attention, sustained research, and continued efforts to address the underlying warming trend that set this entire chain of events into motion in the first place.